All right, well, let's have a look here. Let me grab my answer key first. So as you can see, I've changed the question a little bit, made it a little bit more simple to sort of answer. It says a skydiver in the spread eagle position opens their parachute. Is the diver accelerated? And you just have to circle yes or no.
Yes.
I'm hearing a resounding yes. Hands up, yes. Everybody, almost. Correct answer, of course, is yes. Which direction? Up, absolutely. Up. Now, why is there acceleration and why is there up?
Because all the wind goes in it.
All the wind goes in it.
Yeah, but the person doesn't actually go up.
That doesn't, you're right. Steve says the person doesn't go up. That doesn't have to happen for there to be upward acceleration. All that's happening is, remember, forces and accelerations are in the same direction. So when the person opens the parachute, is there a force up? Does the person slow down?
Yeah.
The person slows down, the velocity changes. Why it slows down? If the velocity is, this is not a free body diagram, if the velocity is down and they slow down, then clearly there must have been a force up. And if the force is up, the acceleration must be up. Steve makes a very valid point. The skydiver does not go upward in the air. You sometimes see that in videos, right? Like, you might see a couple of skydivers. One's got the camera, the other one's there. Pulls the ripcord. The guy that pulls the ripcord does what? Do they really go flying up like that?
No.
What happens?
They slow down with the camera.
Yeah, they slow down, but the camera keeps going. Exactly. So, yeah, there is an upward acceleration, but it only causes them to slow down. It doesn't cause them to go upward. Okay, let's look at the weightlifter. There's my weightlifter picture. A weightlifter lifts a 115 kilogram barbell from the ground. How does the force exerted by the lifter compare with the weight of the barbell? Is it more? Is it equal? Oh, sorry, is it less? Is it more? Or is it equal?
More.
Hannah, what is it?
1 second.
Maybe it's on your phone.
More.
I didn't get it.
Oh, maybe.
1 second, let me think.
If we have 150, okay. If we have 115 kilograms down, that would convert to, how would I convert that to newtons, Jake? Times by 9.8. Let's just say that's 10, and let's round that 115 to 100. It's approximately 1,000 newtons, right? It's not exactly 1,000, it's approximately 1,000 newtons, right? How does the force exerted by the lifter compare with the weight of the barbell? Well, if it's not more than 1,000 newtons, what's going to happen?
It's going to fall.
Nothing. If the barbell is on the ground and it weighs 1,000 newtons and I lift with 500, what's going to happen? Nothing. Nothing. The only way to get it going is to have a force that is greater. However, that is only true at the start. Once you get it moving, a force is no longer needed to keep it moving. All you need is enough force to overcome the gravity, the weight, and so then you would only need, if it was 1,000, you would only need that 1,000 newtons, right? So at the start, you need like 1,200 to get her going, and then 1,000 to keep it going. Again, it's the same idea as that bicycle one that we talked about before, right? You have to accelerate it to begin with. How does the force exerted by the lifter on the barbell compare with the force exerted by the barbell on the lifter? If I apply 1,200 newtons of force to the barbell, what does the barbell do to me? Apply 12,000 newtons of force on me. Those would be, for sure, would be equal. That's the whole Newton's law one, right? Equal and opposite. Equal and opposite. Okay, suppose you put a wooden block against the wall and push horizontally to keep it falling. You like my picture? Took me a while to make that.
Yeah, that's actually a good picture.
It's not bad, eh? Draw a diagram showing the force on the block and the causes of those forces. Pay special attention to the normal weight force and the weight of the block. Are they in the same direction and are they equal? Well, which way is gravity? Down. That we can agree. The weight force is down. Which way is the applied force?
Towards the wall.
To the right. I'll draw it like this. Right? Now, what else is there in here?
Friction.
There is friction and there is a normal force. Which one is the normal force? Which way does the normal force go?
No, not
The normal force, remember, is always
to it.
perpendicular to the surface. So the normal force, and I should be labeling these, shouldn't I? This red one is the applied force. The blue one is the weight force. And the black one here, this is the normal force. And that FA and that FN should be what?
Equal.
Equal. What then holds the block up from sliding down?
Friction.
Friction. And actually, what you're doing here, when you're holding that block or whatever it is, right? Sleeve of tennis balls, what have you, against. What you're doing is you're increasing the friction force by doing what? By pushing on it. You're increasing the friction, which does not allow it to slide. Okay, if I don't push hard enough, what happens? It falls. Right? If I don't push hard enough, it falls. Which way is the normal force? Out. Why is the normal force out? Because it's perpendicular to the surface. Perpendicular to the surface. And you're still not convinced, I can see. Which way would it move if there was no friction? Down. It doesn't move, therefore there must be, in which direction? Up.
When you press does the friction increase because you increase the mass of the object?
I like the way you did that. Yes. Okay? What Jake is saying is like, let's say this weighs 100 grams. Okay? If it's sitting on the ground, is it easy to push that? Well, sure, it's 100 grams, right? No big deal. But if I put something really heavy on top and then try to push it, what happens? I'm increasing the friction, right? You know how like a piano's hard to move, right? A violin piano like this is hard to move. It's heavy, right? A lot of friction. If I took some papers out, it'd be a lot lighter and it would be easier to move. Not only would it have a lower mass, which would require a smaller force, but there would be much less friction. The friction is dependent upon the normal force up, which is equal to the weight force down. If I try to move something heavy and I kind of lift it a little bit, does that help move it? Absolutely. You're reducing friction. So in this case here, when I push the sleeve of tennis balls or the block, I'm increasing the mass, I'm increasing the weight force against the wall, which is increasing the normal force back, which is increasing the friction. Yeah. I mean, there's also friction between my hand too, right? Yeah. Okay. Explain why an aluminum ball and a steel ball of similar size and shape drop from the same height reach the ground at the same time. Surface area is practically the same. They are of similar size and shape. They're going to plow through things relatively pretty much the same. And acceleration is the same for all objects, isn't it? Right? Acceleration is the same for all objects. They will reach their terminal velocity at the same time. Now, if these are relatively small, like if it's like a steel ball about maybe an inch across, 2 or 3 centimeters across, and a very light aluminum ball, then that light one would be like a piece of paper, right? It would sort of reach terminal velocity quicker. But if they're a reasonable large size, that question's kind of.
Yeah, you can't really.
Yeah. I should maybe change it to like a ping pong ball, right? And then it would not be the same time, would it? Give some examples of following objects for which air resistance cannot be ignored. What are some things where you must include air resistance when talking about it? Paper, ping pong balls, coffee filters, person with a parachute, exactly. Anything that has a relatively large surface area to mass ratio. A piano, if you drop that out of an airplane, would we have to worry about air resistance a whole lot? It's pretty heavy. The surface area is big, but its sort of heaviness overcomes its surface area-ness. Okay, not sure what's happening there. Give some examples of following objects for which air resistance cannot be ignored. Oh, whoopsie. What are some? Yeah, that was not good, is it? Just got to move some stuff out of the way. No, no. Okay, well, I'll have to work around. Oh, now I'm really in trouble. Escape. Give some examples of following objects for which air resistance can be ignored.
A heavy piano.
A heavy piano. An arrow. Things that are very aerodynamic. Exactly. Maybe a pencil on end, although eventually it would sort of flip on the side. The value of G on the moon is 1/6 of its value on Earth. It's 1.6. Joey, you need to watch. Will a ball dropped from the same height by an astronaut hit the ground with a smaller or larger speed than on Earth? Let's read this question again. This is hard. The value of G on the moon is 1/6 of its value on Earth. Will a ball drop from the same height by an astronaut hit the ground with a smaller or larger speed on Earth? So it's landing, it's traveling the same distance. One is an acceleration that is much smaller than the other. I'm asking which one will hit the ground with a larger speed. Will a ball drop from the same height by an astronaut hit the ground with a smaller or larger speed on Earth? Smaller or larger? Smaller. Larger. Don't know.
That's cheating.
How can we figure this out? How can we figure this out? We're going to make some assumptions. Can I just assume that it falls from a certain height? Can I just do that?
Yeah.
Why not? I'm in charge of this little question. I'm going to say the distance is 1 meter. Why do I pick 1 meter instead of, I don't know, 1.43? Yeah, because it's simple. Exactly. On Earth, the acceleration is 9.8. On the moon, the acceleration is? Do I need to worry about them being negative? If those are negative, then my displacement is also negative. Why? Because it's down. Okay, so let's just see which one hits the ground faster. Now, prepare to have your mind blown a little bit here. V bar equals d over t, right? V bar is equal to 1 over t. Let's just make everything positive, and then we'll see if I need a negative in there or not. What's the average velocity? What's the initial velocity when I drop something? 0. Would you agree with me then that the average velocity is going to be the final velocity divided by 2? Can I say that?
Yeah.
Notice how I'm lining everything up here. So, Vf over 2 is equal to 1 over t. Haven't really got anywhere because I have how many unknowns? 2. Would you agree that the Vf is also equal to the delta V? Because the Vi is 0?
Yeah.
You would agree with that? So delta V over 2 is equal to 1 over t. And knowing that A equals delta V over delta t, could I then say that delta V is equal to A? And if I just get rid of the delta, could I just say delta V is equal to AT? Are you comfortable with that?
Nice.
I've got A equals delta V over delta t.
Yeah, I can.
Can I rearrange that so I have delta V equals A times t? And then can I take this and plug it in there? By the way, this is why you take pre-calculus math.
I don't think you can.
Yes, I can.
I don't think you can.
Yes, I can, because this delta V and that delta V are the same. And so now I'm going to write in blue AT over 2 is equal to 1 over t.
Are we going to get questions like this? This is ridiculous.
No, you're not going to see this. I'm proving a point. All right. Do I have a value for A? I sure do.
Have a T or a D.
I don't need. All I've got now, so I can put, do we want minus, or we're just going to go 9.8? Let's just go 9.8. Make it simple. 9.8t all over 2 is equal to 1 over t. Now look carefully. What have I done? I've got rid of one of the unknowns, and now I just have one, which is t. Now, granted, I do have two t's, but can I combine them somehow together, do you think? Every kid loves to cross multiply for some reason.
Yeah.
Cross multiply. 9.8 t squared is equal to? I took 9.8 t and I multiplied by t. 9.8 t is equal to? Cross multiply. Can you solve that, grade 11 students?
Yeah.
I sure hope so. T squared is equal to 2 over 9.8. T is equal to the square root of 2 over 9.8. Go ahead, do the math, someone for me. And
I think we should just leave it as t.
this, my friends, is why you write the formula and why you line up the equal signs, because you will be expected to be able to do similar kind of things, not right away, but soon. I'm foreshadowing here for you.
I was gonna say, I would need like 3 places to be
Now, all I've done there, did I get the right answer?
I don't know.
I hope so, because I've been given that answer for a lot of years.
Oh,
You would go 2 divided by 9.8, right, equals, then you got to take the square root of that. It's right, 4.45 seconds. All of that is how long it takes for something to fall from 1 meter at an acceleration of minus 9.8. Now, Joey, does all of this logic hold true for things on the moon? Like, would anything change here because I'm on the moon?
yeah.
Only one thing. What would it be?
Acceleration.
The acceleration of 9.8. Can I just say on the moon, can I just go 1.6 t squared is equal to 2? Is anything going to be different? All the laws are the same, right? I just replaced that 9.8. And so what is my t value going to be on the moon? Well, it's going to be different, isn't it?
2 over 1.6.
Right? It's going to be the square root of 2 over 1.6, which is 1.12 seconds. It's considerably longer. Is it 6 times longer? You don't need to do the math, I hope, to realize it's not 6 times longer, is it? Not even close, right? 0.45 times 2 is 0.9, times 4 is going to be 1.8. It's definitely not 6 times. Okay, now if I'm not mistaken, the question was way back when, will a ball drop from the same height by an astronaut hit the ground with a smaller or larger speed than on Earth? I still don't know, but I do know the answer to B, don't I? I should have B first as my question there. Because B said, will the ball take more or less time to fall? On the moon, it will take lots more.
But how would we know that it's supposed to be on the moon in that question? It doesn't even say.
The value of G on the moon is 1/6 of its value on Earth.
Yeah.
Will a ball drop from the same height by an astronaut, hit the ground with a smaller or larger speed than on Earth, and will the ball take more or less time to fall? We're talking about on the moon. Okay? So, clearly it will take more time, but will it hit the ground with a smaller or larger speed?
Well, the circle is large, so it must be large.
How am I going to determine that? Well, you'll notice that one of the things we want to really find out what VF is, don't we? Isn't that what we want? It shows it right here. VF over 2 is equal to 1 over T. There's our formula right there, right? So on Earth, it's going to be VF over 2 is equal to, and I'm doing a very bad thing here by writing my stuff way up top here.
Wow, what's wrong with that? You haven't nailed.
My T down here is, on Earth, is 0.45. So VF is going to be 2 over 0.45. Somebody? What's 2 over 4.5? How much? 4.4. On the moon, what would change? Would anything change? The time. It would be 1 over 1.12. Clearly it's going to be different, isn't it? 1.78 meters per second. It will hit the ground at a much lower speed, and it will take much longer. Do you remember the video where the astronaut dropped the feather in the hammer? Did it look like it was falling slower?
No.
You don't remember?
We were just so transfixed.
I think we should watch the movie again.
Yeah, no, it was clearly going. It took a lot longer, and it was going a whole lot slower.
That
So
question would be like 20 marks.
I would not expect you to be able to do that yet. I'm not going to ask you that question. I'm
But
just,
if you
I'm
did,
just
would it
sort
be
of.
like 20 marks?
Oh no.
Yes, and then like until next.
But this is what grade 12 physics students are going to be doing: is moving, manipulating formulas like that. Or they don't like it,
That
but
would take me hours.
you'll soon be able to do it, no problem. But practice your math skills. You're going to need them. Okay, moving on. Number 8. Very similar kind of question. A ball is thrown vertically upward with the same initial velocity on Earth and on planet Alpha, which has 3 times the gravitational acceleration as Earth. I'm going to have to do the same thing. How does the maximum height reached by the ball on Alpha compare with the maximum height on Earth? Will it be more, less, or the same? Okay, so I take my tennis ball, I throw it upward with the same initial velocity, like 10 meters per second. I do it on Earth. I go like this, then I jump in my spaceship when I go to planet Alpha, 3 times the gravity, and I throw it just as hard. Does it go higher, lower, or the same? Your gut probably tells you lower, right? Can we prove it? Well, sure we can. We're going to do it right over here. You can do it.
It'd be faster just to go to Alpha and throw.
Oh yeah, it'd be faster. Does it matter what initial speed I pick? As long as they're the same, right? Planet Earth, we're going to say 9.8. Planet Alpha, 3 times 9.8.
About 26.
29? 29.4? Okay, so suppose I use an initial velocity of 10. Why would I pick 10? 10's easy. 1, 10, same thing almost, really. Okay, what's the average velocity if I throw the ball up? I start at 10 and I end at 0. My average is going to be 5. Okay. What is my delta V? If I start at 10 and go to 0, my delta V is? Negative 10. Now, do you get the feeling that we might have to worry about this being negative?
Yeah.
Because this delta V is negative 10. Do you get the feeling that that should be negative?
Yeah.
I think I get that feeling. I'm going to plug it in there. Okay, I'm going to go A equals delta V over delta T minus 9.8 is equal to minus 10 over T. Hey, I can find out the time. It's what? 1.02 seconds. Minus 10 divided by minus 9.8. So it takes about 1 second if I throw it at minus 10, or throw it at 10 up. V bar is equal to d over t. The average velocity is actually, is the average velocity minus 5 or is it 5? It would be 5 because it's up, right? So 5 is equal to d is what I'm trying to find. My time is 1.02. So the ball actually travels a little over about 5.1 meters high on Earth. Can you do the same thing on planet Alpha? It's going to be exactly the same thing, right? It's going to be all that, and then I'm going to have A equals delta V over delta T. Now I've got minus 29.4 is equal to delta V over my time. No, I don't have my time. That's what I'm solving for. Sorry, that's what I'm solving for. Got a little sidetracked there. I was thinking ahead. This is going to be minus 10 T. The time on planet Alpha is going to be 10 over 29.4, which is 0.34 seconds. It's going to take a lot less time for it to reach its peak. How come? Because the acceleration is so much greater. It's pulling it down. But how high does it go? I only threw it at 10 meters per second. It's only going for 0.34 seconds. Do you already realize it's going to have to be less?
Yeah.
It's going to have to be, right? V bar is equal to D over T. The average is still 5. D over 0.34. And yeah, my D works out to a much smaller number, about 1.7 meters. Kind of work that out for me. Is that 3 times higher?
Yeah. 3 times lower.
Is it, or 3 times lower? How are you going to do it, Hannah? Is 5.1 3 times bigger than 1.7? Yeah. You got a calculator there. Just divide, don't you? Oh, I thought you've been punching on your calculator there.
No, I'm looking at my.
Oh, okay. So 5.1. Yes. It's 3, isn't it? 3 times lower. 3 times lower, which is to be expected. Now, the real kicker is the next question, which says, if the ball and alpha were thrown with 3 times the greater initial velocity, how would that change your answer? What if instead of throwing at 10, I throw it at 10 on Earth, but over here on planet Alpha, I throw it at 30? I'm going to have minus 29.4. Instead of minus 10, I'm going to have minus 30. My T is going to be the same. What do you think? Is it going to be the same height, 5.1?
Yes. Yes.
Most people think so. But remember, the average velocity is now not 5. The average velocity is, I should move this out of the way a little bit. What's the average velocity if I go from 30 to 0? So now it's going to be 15 is equal to D over 1.02, and D is around? No, it's 15.3 meters. 3 times higher. It's not the same.
What would you have to throw it then?
Oh, that's a real tough question. I'm not going to even answer that one.
No idea.
Could you figure that out?
Like 1/3 of the higher? I don't know.
Well, how would you figure it out? You'd take this 5.1 and you'd plug it in there, right? And you'd have to work backwards to there. And you might even get up with a... Have you done system of equations?
No.
Yes, you have.
Oh, yeah.
In grade 11, you probably got it by now. So you maybe haven't got grade 11 math, maybe you haven't seen it. Have you done equations where you get like a line like this and a line like that? You have to find out where they intersect? Something like x plus y equals 10 and 2x minus y equals 15.
Yeah, we should plug into a calculator.
Oh yeah, grab the calculator. Right? Yeah. Okay, well, that's basically what these kind of things are, is that it's 2 equations with how many variables? That's what these are, just a little more complicated. All right, I can see I'm losing you.
Yeah. I'm lost.
Let's go on. Is there one last question? Or is that it?
There's one next.
You know what? Let's read number 9.
Oh, for sure.
Let's read it.
Rock
For now. We'll get back.
Rock B is thrown down.
We'll come back to it.
You reach the block, which rock has the greatest velocity.
I'll come.